So remember last time we talked a lot about the detail of circuits in the two-dimensional rigidity matrix. These R2 circuits, we from Lemans' theorem, we knew exactly what graphs these circuits were. And we spent a lot of time looking at structural results to find that you could always have a degree-free vertex in a circuit and reduce your circuit to a smaller one. So this doesn't completely give you a recursive construction, but so that's the first thing I want to do is say a little bit about that problem, because we assumed free connectivity to make that work. And so I have to talk about what happens if you're not free connected. And then we'll start thinking about the more general case of free connected redundantly rigid graphs that are not necessarily circuits. And it turns out that these are much more complicated than just saying you take a circuit and you add some edges in. There can be much more complicated structure to the graphs. Okay, so what do I start saying here? So we've shown that if the circuit is free connected, then it has an admissible node, okay? But I want to, first of all, and I said this briefly last time, I want to comment that the containing one admissible node is not best possible. So what Berg and Jordan proved precisely was that as long as you have at least 5 vertices, your free connected circuit has either 4 admissible nodes or 3 pairwise non-adjacent admissible nodes. I won't go into the proof, but this is just an example to illustrate that what they found was actually best possible. So here the 4 blue vertices are admissible, and here there is only 3, but they're pairwise non-adjacent, and all 3 of those are admissible. Okay. But what I do want to spend a few minutes on is the case when the circuit is not free connected. So it's easy to check that all R2 circuits are 2 connected, and it's also not so hard to show that if they do have a 2 vertex separation, that there's no edge between those 2 vertices. So the 2 vertex separation looks like this one you can see here. And hence what we're going to do is use this operation that I'm showing in this picture. So to deal with 2 but not free connected circuits, we go back to the 2-sum operation we saw earlier. So the 2-sum operation took 2 circuits. In this case, it's 2 copies of K4. And you pick an edge E in one of the copies and an edge E dash in the other copy and identify them and remove the common edge. So the end vertices of E, U, and V become the end vertices here, and the end vertices U dash, V dash are identified with them. So U and U dash becomes this one new vertex here. And similarly, V and V dash become a new vertex, and the common edge is thrown away. So this is a standard Metroid operation, but it's going to be exactly the one we're going to use to generate all R2 circuits. Notice that this is not going to be helpful for global rigidity because the 2 vertex separation shows that this graph is not globally rigid. So the result of the 2-sum operation is never going to be a globally rigid thing because it always introduces failures of free connectivity. But it's just interesting on its own, I think, to note the recursive construction of the general class of circuits as we go. So here it is. This theorem was in the Berg-Jordan paper. So a graph is a R2 circuit if and only if it's a connected graph which you can obtain from vertex disjoint copies of K4. So it might be you need many, many copies. It might be you only need 1. It depends on the particular graph you're interested in. But it's obtained from some number of vertex disjoint copies by taking 2 sums of connected components. And within any connected component, you can apply as many 1 extensions as you like. But notice I never took 2 disjoint components and did a 1 extension, deleting an edge over here and adding a new vertex that was adjacent to the second disjoint component. It was always 1 extensions within connected components, and the only way I took 2 disconnected graphs and connected them together was by the 2-sum operation. Okay, so let's do the proof. And by do the proof, I really mean I'll say about 2 lines and leave it as an exercise. Okay, so a connected graph constructed in this manner is an R2 circuit. We know the 1 extension move preserves the property of being a circuit, and the 2-sum move also does. So the other direction is the non-trivial part. Here we use induction on the number of vertices. Suppose we've got at least more than K4, so at least 5 vertices. Then here's an exercise, and really I just said it. If an R2 circuit has a cut pair, XY, then it's not so hard just to do a little count and prove that it must be that the 2 vertices in the cut pair are not joined by an edge. And with that, you can then see that if you have a two vertex separation, you separate out into the two parts and add the edge on both sides, you result in two circuits. So adding XY to each side gives you an R2 circuit on each side. So you start with one with this two vertex separation, you break it into two smaller circuits. So this is an exercise if you want to check, but it's just some counting argument using the fact that circuits are graphs with E equals 2v minus 2 and I of x is at most 2x minus 3 for all proper subsets of V with at least two elements. If you're just using the counts on both sides, you won't find it so hard. But that exercise tells us exactly what to do whenever there's a two vertex separation. So from the exercise, you can assume that the graph is free connected. And then all the work we did in the previous two lectures tells us that either the graph is K4 or it has a vertex of degree 3 we can reduce by a 1 reduction, and hence we're done. Okay, so I think it's nice just to observe the full recursive construction of circuits. As we talked about last time, what we actually need for the global rigidity application is for our admissible node to be feasible, to preserve free connectivity as well as the circuit property. And then we need to extend that to look at redundantly rigid and free connected graphs instead to do the whole case. Okay, so yeah, so first of all, I guess I want to talk about this feasibility. Maybe I didn't mention feasible last time. So maybe what I just said about feasible didn't make much sense, but it's here. So I'll say it in more detail. So we know that we want all of our globally rigid things are going to be free connected. But it's possible, since circuits can be two connected but not free connected, that I take a nice free connected circuit, do a 1 reduction on it and break free connectivity. So that's going to be bad because then I reduce to something we know is not globally rigid. So we're not going to be able to say this smaller thing is globally rigid, one extension preserves global rigidity, hence the bigger thing is globally rigid. Okay, so what we want is our admissible node that we reduce to a smaller R2 circuit with, we want it to also preserve free connectivity. So what we do is we say that in a free connected R2 circuit, the node is feasible if there is an admissible 1 reduction at that node, adding some edge among the neighbors such that the graph you obtain is free connected as well. So feasible means admissible plus preserves free connectivity for the particular, for some of the 1 reductions. So maybe there are 3 different 1 reductions at the vertex. One of them fails to preserve admissibility. One of them preserves admissibility but not feasibility. But as long as one of them preserves admissibility and feasibility, we're happy. Okay, so here's a small example. In fact, this is an example in the Berg and Jordan paper. So here, if you look at this vertex V, this is a R2 circuit. I'll let you count up for yourself if you like. Look at the vertex V in blue. If I remove V and add one of the edges, then what can happen? So suppose we added this edge here, then V would have disappeared. So what we'd be left with, so when V disappears, this edge would go. And so this vertex and this vertex would separate this one and this one from the rest of the graph. So we would create a 2 vertex separation. So if you look at V, you remove it and its 3 incident edges, then you would see there was a 2 vertex separation which removed these 2 vertices from the rest of the graph. And similarly, it's sort of symmetric, so you could say the same thing about this one. And you can also talk about adding that one, but then that one would leave a 2 vertex separation in here because this edge would have disappeared. So I don't know how clear the colors I'm scrolling on here are, but in each case, if you just draw the picture yourself, you'll see that all 3 possible 1 reductions at V result in a not free connected graph. However, in this particular graph, there are other vertices of degree 3, for example, these ones. And so you can check and go through and see that actually at least one of them preserves free connectivity. But just this was to show that do exist. This bad thing can happen sometimes. So we have to make sure that at some point it doesn't. Okay. But when I say we have to make sure, I'm actually going to omit any more of the detailed combinatorics from this course and say that what happens is that Berg and Jordan proved that it's okay, that if you're free connected, then in fact you get two, not just one, but you must be able to get two non-adjacent feasible nodes. So they improved the admissibility thing. We've talked about the last couple of lectures to show, in fact, you can always find an admissible node that preserves free connectivity as well. Okay, but then so now we know how to stay within the class of free connected circuits. So that does immediately give us the theorem that we want for the special case of R2 circuits. So their result says that a graph is a free connected R2 circuit if and only if it can be constructed recursively from K4 by a sequence of 1 extensions. Okay, so we know we can get every free connected R2 circuit from K4, which we know is globally rigid, by a sequence of 1 extensions, which we know preserve global rigidity. Hence, we have the nice corollary that every free connected R2 circuit is generically globally rigid in 2 dimensions. And so Berg and Jordan's paper is called a proof of Connolly's conjecture because Bob Connolly conjectured this, and then obviously they proved it. Okay, so that's sort of the end of circuits. And now I want to move on to the more general case of free connected redundantly rigid graphs. But does anyone have any questions about the circuit case before we progress? Okay, I am watching the chat, by the way, if anyone prefers to type a question. Okay, so I'll say what M connected means in a moment. It's a particular type of graph, but M is for a matroid. It's a particular matroidal property that we're going to put on the rigidity matroid and have a class of graphs satisfying this matroidal property. But we'll get to what it is in a moment. So this is all just sort of repetition. We want to show that free connected redundantly rigid implies globally rigid. We've dealt with the minimum case, so the smallest number of edges you can have and be redundantly rigid is E equals 2v minus 2. But if you're redundantly rigid and have that number of edges, you're exactly an R2 circuit. So if you're free connected as well, then you're a free connected R2 circuit, and we just talked about that case. So now we want to look at redundantly rigid free connected graphs that aren't necessarily R2 circuits. Okay, so here's the matroid connectivity idea. So we say a graph, and I'm only defining it, this is a general matroid theory idea, but I'm only going to define it for the rigidity matroid, the 2-dimensional rigidity matroid. But it's a general concept in matroid theory. So we say a graph is R2 connected if every pair of edges of the graph, so this should be a graph, this is a graph G, is R2 connected if every pair of edges of G belong to a common R2 circuit. So you tell me the edges E and F in the graph, and I have to be able to show you an R2 circuit that contains that pair of edges. So for example, if the graph is a circuit, then the whole graph is a circuit, every edge is in the circuit, so it's automatically connected. But it might not be a circuit, and so this is sort of a generalization of circuit, okay? So we have to show that this is a natural generalization of circuit, but why is it relevant to our problem? Well, we're going to do that with a lemma and then a theorem. I'm going to show really that it's equivalent to redundant rigidity, at least for free connected graphs. So one direction is quite easy. So suppose a graph G is R2 connected, so every pair of edges is contained in some circuit, then the graph is redundantly rigid, okay? Right, so here's I can't fit it all on, but it's a short proof. So why is this true? Since I'm R2 connected, every edge is in a circuit. Circuits are rigid by the Leman-Polacek-Geringer theorem. So my graph that's R2 connected must contain some redundantly rigid subgraph because every circuit is redundantly rigid and it contains circuits because every pair of edges must be in a circuit. So we are able to choose a maximal redundantly rigid subgraph and call it H. So what I was just saying was why this maximal redundantly rigid subgraph exists. There must be something redundantly rigid, which take a largest one, okay? H is a vertex-induced subgraph, otherwise add the edges in and it's a larger subgraph. So what's true is either H equals the whole graph, this maximal redundantly rigid subgraph is everything, but then we're done because that's what we want to conclude, or the vertex set of this maximal redundantly rigid subgraph is strictly contained within the vertex set of G, okay? But in this second case, there are edges in G which are not in H. So let A be such an edge and choose some edge F in H. R2 connectivity tells us that there is a circuit containing E and F. And we're going to use that to get what we want, to contradict the maximality of H, I think. So since G is R2 connected, there is a circuit, C, containing this pair E and F. So E was in G not H, and F was in this maximal redundantly rigid subgraph H. So we've got some circuit C containing E and F. Okay. So the number of vertices in H intersecting the number of vertices in C is at least 2. So why is that? Well, why is that? That was easy to me before the lecture. Why is that? Oh, because it's R2 connected. So it's R2 connected. So we have this circuit C that contains the pair E and F, but F was in H and F has 2 end vertices. So those 2 end vertices are in the intersection. So it's at least 2. So both the end vertices of F are in this intersection. But if you take 2 things that are both rigid in the plane and they intersect at least 2 vertices, the union will be rigid. So H union C is rigid. So we want H union C to be redundantly rigid to contradict the maximality of H. We now know it's rigid. If you're rigid and every edge is in some circuit, then you're definitely redundantly rigid because you're rigid and you can throw any edge away. It'll be in a circuit, so it won't change the rank when you delete it. But that means that we're done because R2 connected graphs, every pair of edges is in a circuit. So certainly every edge is in a circuit. So I say it here. So H union C is rigid. Since every edge of H union C is in some circuit, H union C is also redundantly rigid and it's bigger than H, so it contradicts maximality and we're done. So we've proved that every R2 connected graph is redundantly rigid in 2 dimensions. Okay? The converse is harder. And in fact, the converse is not true in general, but we need this free connectivity assumption. Or we're going to use something very close to free connectivity, in fact, to get a best possible kind of result. So here's an example which shows that in general, M connectivity, and in our case, what I mean by M connectivity is R2 connectivity, is a stronger property than redundant rigidity. So here's the example. I've just taken 3 K4s that intersect in this sort of triangular way. So there are exactly 3 circuits in this graph, the 3 copies of K4. Okay, so each copy of K4 is a circuit. It's not hard to see that there's basically nothing else. Okay, it's also not hard to see that you can generate this thing by 0 and 1 extensions from a triangle. So it's by the Leman theorem, say, instead, if you like. This is a rigid thing. So every edge is in a K4, which is a circuit, so it's rigid, and every edge belongs to a circuit. Hence, this graph is redundantly rigid. But I claim it's not R2 connected. So for example, choose this edge E here and this edge F here. Then the pair E and F, all the circuits are K4s and they're not in the same copy of K4. So there is not a common circuit that contains E and contains F, because the only circuits are the K4s. So this is an example of a redundantly rigid graph, which is not R2 connected. So it is a different property. But what we're going to see is that the 2 vertex separations like this or like this pair are exactly why it's not. And if we're free connected, it would have been both at the same time or neither. Okay. So just we could just do this for free connectivity. We don't really need this nearly word, but this is what they did, and this is the result from Bill Jackson and Tibor Jordan in 2005. And it's no extra work really to include this nearly word, so I did. So a graph is said to be nearly free connected if G can be made free connected by the addition of at most 1 new edge. So it might have a 2 vertex separation, but if I just add one edge in, I'm going to get back to being free connected. Okay. So what's their result? If you give me a nearly free connected graph, then the graph is redundantly rigid if and only if it's R2 connected. And so this will allow us for free connected graphs to translate our redundant rigidity free connectivity problem into a R2 connected and free connected problem. Okay, so we've just shown that every R2 connected graph is redundantly rigid. That's the easy direction, but now let's do the harder direction. Okay, and it's really going to be a little bit of setup and then one sequence of equations. Okay, so suppose our graph is redundantly rigid, but not R2 connected. So we can think about the R2 connected components within our graphs, i.e. the maximal R2 connected subgraphs, and we're going to call those R2 components, okay? So our graph is not R2 connected, so it has some number of components, some number of maximal R2 connected subgraphs. Let H1 to HQ be all of those components, okay? And now we need some definitions, or it's just some notation, I guess. So let Xi be the vertex set of the R2 component Hi minus everything that's in some of the other Hj's. So Xi is the set of vertices in Hi which belongs to no other R2 component. And then Yi is the vertices of Hi minus the ones that belong to nothing else. So in particular, you could look over here. So maybe you have the 4 black components that you can see there. Then the blue areas are the parts of each Hi which are in nothing else. So they're the Xi's. And the green parts are the ones that are in something else. So they're the Yi's. Okay? So hopefully that sort of picture makes the notation a bit easier to digest. And then I want to have some letters to simplify the equations that follow. So Ni is the number of vertices in the R2 component Hi. Xi is the number of vertices in the set Xi, and Yi is the number of vertices in the set Yi. So obviously we've just split Ni up into Xi and Yi, so we have this. Xi plus Yi is Ni. And the number of vertices in the whole graph, we go through all of the components, so we have to add up all of the Xi's, all of the blue bits. We get to take all of the parts that were in Hi but nowhere else, and then we want to add up the others, but it's a bit more complicated because some of the greens could have been in many different places, so we just take the union of all the green sets instead. Okay, and we can say one more thing about the Yi's is that we know there's at least 2 vertices in common between any Hi and the rest of the graph. So actually we can say that the sum of the little Yi's is at least twice the size of the union of the Yi. Okay? Okay, so this is all set up, which I'd really like to have on a board in the top of the wall that we can then use in the equations, but we'll just try and remember it. Okay. So I guess there's a few more words yet. So every edge of G is in some circuit, and every circuit has at least 4 vertices. So every one of our maximal R2 connected components has at least 4 vertices. So Ni is at least 4. Since we're nearly free connected, we know that Yi, the number of bits shared from Hi with the rest of the graph, is at least 2 for all of our Q different R2 components, but because it's nearly free connected, it's actually at least 3 for all but at most 2 of them. So this is where I could just say it's greater than or equal to 3 for all of them if I just cared about free connectivity, but because we want this nearly word, we just have this one extra little bit for 1 or 2 of the sets. But you'll see that that's not going to cost us anything in the end. Okay. Each R2 component is definitely redundantly rigid. So each R2 component has the rank of the rigidity matrix as the right thing for it to be rigid. It's 2ni minus 3. Okay, and you can, I've done P restricted to HI. You can imagine there was some generic framework P, because I never said a P in the statement of the lemma. Okay, so here's an exercise. So I mean, it's not so hard. I just didn't want to try and do this part in the proof because I thought it was a slight distraction from the main thing I was getting across. So I want you to show that the rank of the rigidity matrix is equal to the sum of the ranks of all of these different HIs. So for example, in this K4 case where there were 3 K4s, take the rank of the 3 different K4s and add them all up. And it would be, what, 5 for each of the K4s in that case. Okay, so now we come to the equations, and I might skip back up if I've forgotten at least. So we want to just look at the rank of the rigidity matrix. We just said we can write it as the sum of the ranks of the HIs, and the rank of the HIs was 2ni minus 3 for each of the HIs. So from there and there, the rank of G is equal to this sum. Okay, but we know what ni is, so we can express ni as xi plus yi. First of all, we'll just simply take the 2 outside and just have the sum of ni, because we just get a minus 3q times, so we can just take that out as well. So now I want to replace this sum of ni with ni is xi plus yi, and that gives me twice the sum of xi plus twice the sum of yi, except I've written that twice the sum of yi separately because I want to split them up, and I've still got my minus 3q, okay? So, okay, so the sum of xi, yeah, so let's go back up. So remember we had this here. So the number of vertices is the sum of the xi plus this, but if we replace the size of the union with the sum of the yi is greater than or equal to it, we can just put an inequality in. So this gives us, from the blue underlined bit here, we get twice the number of vertices, twice xi plus yi, gives us the 2v. The sum of the yi, this gives us 3q minus 2. The 3q is because it was at least 3 connected for all but at most 2. So 3q minus 2, where the minus 2 is taking 1 off for the other 2 to get down to where it could have actually been 2 vertices in the intersection, and then the 3q continues on. Then of course the 3q and the 3q cancel and you get 2v minus 2. So what we've said is that the rank of the rigidity matrix is equal, greater than or equal to 2v minus 2, which is strictly bigger than what the rank can possibly be. So we've got a contradiction. So we've contradicted the fact that the rank of the rigidity matrix for any rigid graph is twice the number of vertices minus 3. So we supposed there were all these different R2 connected components, and we found a contradiction. So there was actually just one, and we were happy. So what we've proved, I said it before, but what we've proved is that if we just look at free connected graphs, and now we're going to forget the word nearly, we're not going to worry about that anymore. If we just look at free connected graphs, then the graph is redundantly rigid if and only if it's R2 connected. So to recursively characterize free connected redundantly rigid graphs, we can just look at free connected R2 connected graphs and see what we can say about those. And you'll see in a few minutes that it gives us a much easier way to understand them than I'm aware of that we would be able to do for redundantly rigid graphs directly. Okay, so the idea, are there any questions about that? So now we've translated from redundant rigidity to R2 connectivity.
Yes, could you just go to the third line of the equation again, please?
Yes.
Oh, okay. Good, I'd read that wrong. Thank you.
Okay.
Okay, that's all, thank you.
Great. Okay, so what's about to follow is an idea from Metroid theory called an ear decomposition. And you can see it has some definition that takes a bit of digesting, but I'm not sure I want you to digest it in a huge amount of detail. What I want you to think is that this definition that's coming of an ear decomposition is a property that R2 connected graphs have, which will allow us to find vertices of degree 3 in an R2 connected graph. And I will show an example after the definition of what happens if the matroid is the cycle matroid, where it really is forget about matroid theory and just talk about graphs. And then it will hopefully be a lot clearer, and you'll see by analogy the kind of idea. But I will go through the definition. I'm just, if you're not so comfortable with matroids or it's not so clear, then I'm sort of saying it's not necessarily a block to your understanding of the intuition that I'm trying to get across in this part. Okay, so we take a matroid with ground set E and independence condition I, and pick some sequence, a non-empty sequence of circuits in this matroid. So it's not necessarily a rigidity matroid of any kind. It's not necessarily one where we understand what the circuits are in any great way, but just some sequence of circuits. And I'm going to take some notation. DJ is the union of the first J circuits in this sequence. And we do this for all possible J's. So there were T circuits, so we'll go anywhere from 1 to T. So this sequence of circuits, C1 up to CT, is called a partial air decomposition of the matroid if for all I between 2 and T, we satisfy 3 conditions. So the first one says that your new circuit CI has to intersect the union of all the previous ones with something, okay? The second condition says that your new circuit minus what's in the union of the previous circuits has to have something new outside. So they're sort of obvious things that you would want. You want to sort of be related to the previous bit and have something new. So they're easy. And then the third condition is a sort of technical one. So the third condition says no circuit satisfying E1 and E2. So this is no circuit CI dash satisfying E1 and E2 has what's missing from when you take away DI minus 1 from CI dash properly contained in CI minus DI minus 1. So somehow you've chosen the minimal circuit you can add to the union of the previous ones to continue on in your path, okay? But as I say, the reason why these 3 conditions are sensible things to be looking at is not necessarily something that you need to worry too much about for the purpose of this lecture. Okay, so and a little bit of notation, the set that you get from the circuit CI by deleting what's common to the previous union of the previous I minus 1 circuits is called the lobe. And we use CI tilde to denote this lobe. We're now following a paper of Jackson and Jordan, by the way. It's their idea to use this sort of matroid theory stuff in rigidity. Okay. So that was a partial air decomposition. We took our set of circuits satisfying these conditions, gave us a partial air decomposition. An air decomposition is one of these partial air decompositions where the union of all the circuits is the entire edge set of the graph. Okay? So for example, it follows that every edge in the graph must be in a circuit, otherwise you've got no chance because otherwise you wouldn't be able to have this. Okay, so as I say, let's think about the cycle matroid. So if M is the cycle matroid, then circuits are just cycles in the graph. So we can just think about graphs and think about cycles within it. And in particular, in undergraduate graph theory courses, for example, the third year graph theory course I teach, we prove that every 2 connected graph has an air decomposition of this sort of form. So here it's not, the conditions are not so complicated because you just draw a cycle. For example, you might draw this one, and then you draw a path that starts at some vertex in the cycle, finishes at some other vertex in the cycle, and goes around. So it's more just about cycles and paths. And really, if you like, what I did there was a second cycle, but the new thing was just a path coming off. And you just keep doing this again and again. And the real crux of this, and the real reason why, well, at least in my head, the real reason why this is a good thing to do, a useful technique to use, is that when you're doing this, so in the case of 2 connected graphs, it's true that the minimum degree is 2. So this would be minimally 2 connected in the sense that if you delete any edge, it still remains 2 connect. Sorry, if you delete any edge, 2 connectivity fails. So it's minimal with respect to being 2 connected. Then it must have a vertex of degree 2, because in the, say this green one I added over here was the last ear in the ear decomposition, the last cycle. Then on this path, every vertex would have degree 2, except for these guys at the end. So you'd have found your vertex of degree 2. The case when it wasn't minimal would be if the last ear, say, was like that, and it added just an edge between existing things. But that would, if you get rid of the minimal condition, you can't have an edge as one of the ears at the end. So the same idea is what we want to do here. We have circuits, C1, C2, C3. We have these more complicated intersection conditions and what's new, etc. But it's the same idea that in the last circuit, when you finish in C3, there is enough new things here that weren't common to what already existed, that you can find some vertex of low degree, and then we can start playing the structural game we played in the last couple of lectures to find a node we can reduce again. Okay. Okay, so let me give you an example with the two-dimensional rigidity Metroid. So here's a graph. It looks a bit like the complete bipartite graph K35, except it has an extra edge between V4 and V5 down here. Okay. So what I could do, I could have my first circuit in my ear decomposition could be everything except for vertex 4. So if I take away vertex 4, then what I have is exactly a copy of K34, which you can check for yourself as a R2 circuit. Okay. Then I could take C2 to be everything except for V5. Okay, so what did we have to check? We had to check that there was some overlap with what we had before. That's clearly true. For example, all of these were common. There is something new that wasn't there before. Well, V4 wasn't there before and now it is, so that's true. And we've only added one new vertex, so it's not so hard to check the minimality condition again. But again, we get a copy of K34 as our circuit. And then as our third one, all we want to do is add this final edge V4, V5. So here the minimality is easy because we just need to have anything that's a circuit and includes that edge. And that edge will just give us something new. So all we need to do is make sure we overlap with something, which is again trivial. So all we really need is to pick a circuit. And if you take the graph and subtract vertex 7 and vertex 8, then what you get is K33 plus an edge between two of the vertices in one of the components. You have all possible things here and you have that edge. And again, that's not hard to check, it's a circuit. Okay. Oh, and I even wrote down what these lobes are, the C2 tilde. So in the C2 tilde was, remember, V4 was the relevant part. So it didn't get V4, V5, but it was the other 3 edges incident to V4 at that step for C2. And then for C3, the only new thing was V4, V5. So that's just this one. So hopefully this example is also a little bit helpful in understanding these ear decompositions. So I mentioned that R2 connected graphs have ear decompositions. This is a general Metroid fact from Coulard and Hellerstein from the 90s. So for any Metroid, it has this connectivity property that every pair of edges is contained in a common circuit, if and only if it has an ear decomposition. So we know that we will have this ear decomposition for our free connected R2 connected graph, and that will help us, as I say, to find vertices of degree 3, basically. Okay, so I think I've just skipped past a sentence or two that I had already said. So obviously it was easy to see that R2 circuits had vertices of degree 3 because R2 circuits all have this equation. So by handshaking lemma, the average degree is strictly less than 4, and 0, 1, and 2 are not possible easily as well. But it's not so easy to come up with a similar bound to this for redundantly rigid graphs, or for R2 connected graphs. So we needed a more complicated, well, we needed a reason why you have a vertex of degree 3, because we want to just use one extension. And so this is what we're going to be able to do. So I need a bit of a technical lemma, which I'm not going to give a proof for, and then we'll see the result. Okay, so I take an R2 connected graph, G, let H1 up to H2, these are graphs, they're the circuits induced by an A decomposition, which is really the edge sets, C1 up to CT, of the rigidity matroid. And if there's exactly one circuit, we know that's an easy case, so let's assume there's definitely at least 2 circuits in the graph, okay? So let's let Y be the vertex set of the final circuit of HT minus what's already come in the previous T-1 circuits, and X be the vertex set of HT minus Y. So Y and X are just really telling us what's new and what already existed with respect to this last circuit. Okay, then this is just technical, so I'm not even going to go into really why it's true. But what I am looking at is I had some circuits, C1 or H1, 2, 3, 4, etc. And then at some point I have my last one, and I have the overlapping part and the new part, okay? So Y is the vertices of this circuit HT, which is not already existing. So this is Y, and this part is X in here. So either part A is true, which says Y is empty. And so if Y is empty, that means there's no new vertex. So essentially all Y added was an edge. And if it's empty, then the lobe has size 1 because it's only just an edge. Or Y is non-empty, and then every edge in the lobe is incident to Y. So that means there's no edge like this. Every edge is like this or this. And again, so half of that is kind of self-evident, and half we're not going to ask you to worry about. And then part B says the size of the lobe, the size of what's new, is equal to 2Y plus 1. So the number of vertices out here times 2 plus 1 is exactly the number of edges in the whole thing. Okay, so but again, it's not so hard either part, but I'm just not going to worry you with it. But here's the theorem that I guess the last result I'm going to mention in this lecture, but this is going to be the key towards using what we used for circuits for redundantly rigid graphs in the next lecture. Okay, so I take an R2 connected graph and suppose that if I delete any edge, I fail to be R2 connected, okay? So I'm R2 connected, but minimal in the sense that if I throw any edge away, I lose my R2 connectivity property. Then there is a vertex of degree 3 in the graph. Okay. We've already talked repeatedly about the theorem being true when you have when the whole graph is a circuit. They're clearly minimally R2 connected, but it's just true for those. So suppose my minimally R2 connected graph is not a circuit, then it has an A decomposition, C1 up to CT, of the rigidity matroid with at least 2 circuits in the A decomposition. And these circuits were edge sets, let the graphs corresponding to them be H1 up to HT. Okay? And as before, Y is the vertices of the last circuit minus the union of what came before, and X is the vertices of the last circuit minus what's in Y, so what existed before. Okay. So by the minimality of G in part A of the above, we have Y is not the empty set, because that's what I've said here. So if Y was the empty set, then the lobe is size 1, so it was just adding an edge. So if we take away that edge, we would get a smaller R2 connected graph, and we'd violate this condition. So we've supposed a way that case can't happen. So we know that Y is not equal to the empty set. Okay, and then this is a standard fact. So it's true that, I think I have mentioned this in the previous lecture, but every R2 circuit is free edge connected. In fact, every RD circuit is D+1 edge connected, for what it's worth. So since the circuit HT is free edge connected, we can use part B. So remember what part B said, that just said that the size of the lobe was like this. So the fact that it's 2y plus something says the average degree in y is a bit more than 4, so we don't automatically win, but because it's only very slightly more, and we have a number of edges because of the free edge connectivity that don't contribute to the degree because their ends are in x rather than in y, the 2y plus 1 and the free edge connectivity takes us to less than 2y really for average degree purposes and finds us a vertex of degree 3 over here. Okay. So that gives us the vertex of degree 3 we want. And then so at the start of the next lecture, I'll just finish slightly early today. I won't move to the next set of notes. But at the start of the next lecture, what we'll do is talk about finding admissible and feasible nodes in R2 connected graphs rather than in circuits. We really won't go into the details. So if you're getting sick of combinatorics by now, we will be moving on to other ideas pretty soon, but I will just spend 5 minutes at the start of the next lecture explaining how, or just at least talking a little bit about the extension from circuits to R2 connected graphs. But really, we've done the heavy lifting now in terms of what we're going to do in this course. There's still a lot of technical stuff if you read the Jackson-Jordan paper, but for our purposes, we've basically got through everything I wanted to get across in terms of trying to get you some understanding of how it works. And we will just quickly next time get to the global rigidity theorem and then start thinking about other things. Okay, so I'm happy to have questions since I'm 12 minutes before the hour, so there's lots of time if you want, or we can just finish up early. So over to you.
I have a question related to the Maximal Metroid's rigidity project, but I'll hold off on that in case other people have other questions. But this sphere decomposition idea thing seems very interesting.
There might not be any others, Daniel. It might just be you.
Wait, I've got one. Sorry. The three-edge connectivity condition, is that between CT and each other CI, or is it? Oh no, is that between HT and each other HI, or is that between HT and the rest of the and DT minus 1?
So HT itself is a free edge connected graph.
Yeah.
So remember I had this split into Y's and X's where you look at, say T is 2, then I have my first circuit and my second circuit.
Yeah.
And then at the end, what I was doing was I was using the count of Y, which was just this part over here. Yeah. So I wanted to be thinking about the subgraph induced by Y and finding a vertex of degree 3 in G that was located in this red part.
Yeah.
So what I was saying, the free edge connectivity gave me was that, say, okay, there's some vertices in here and some vertices in here.
And those two sets are.
But because it was free edge connected, there was at least 3 edges across here, which gave me at least 3 things that didn't count towards the degrees in the 2y plus 1. So it was just enough to push the 2y plus 1 under and apply handshaking.
Yes. Okay. Thank you.
Daniel, I guess it's on for you.
Yeah, so have you thought about this ear decomposition idea as a way to understand like maximal matroids with, a set of prescribed circuits, right? Like I know obviously a circuit itself is not going to have a very nice or interesting ear decomposition, but like you know, if you're in, say, the minimal, you know, Metroid with respect to, yeah, K4 and K33, right? Like, and you have a circuit in that, like, you know, if you add some edge, you're, you know, maybe you're too connected, or sorry, maybe you're connected in the corresponding Metroid, maybe you're not. But like, yeah, I don't know. Is there, I guess, have you thought about like using ear decompositions to kind of get a handle on this? I mean, is this, or is there like this seems like a nice tool for this, but if, you know, you haven't thought about this and Shinichi and Bill haven't thought about this, I'm worried it's doomed. So yeah.
Yeah, so I've never even thought to try. So maybe I should think about it a bit. But as you say, that Bill who came up with with Tibor came up with using ear decompositions in Rigidity.
Mm-hmm. Maybe
Would have thought about that quite quickly in their sequence of papers for maximal Metroids. So maybe there's somehow that's implicit in some of the stuff they do, or maybe it doesn't work. I'm not sure.
Okay.
You know, I don't immediately see a way to get started using it for maximal Metroid problems.
I mean, I guess like it would come down to like take a circuit that's not one of your prescribed circuits, add an edge. Maybe that's too connected, maybe it's not. If it's too connected, it has an ear decomposition, and then keep going. And then maybe you get to something, you know, a way to essentially like generate your circuit from your like things that you assert are circuits. I don't know what this set needs a name. This you know, yeah, set of circuits you start out with.
No, I don't think I have a good answer for you, but it's an interesting point to think about a bit. So, I mean, so when you're doing maximal Metroids, at least in my head, I'm usually thinking about independent sets or about circuits. And both cases don't have interesting ear decompositions. It's only when you're very redundant that you have lots of circuits and lots of interesting ear decomposition to play with. And in that case, I don't know what you can actually learn about the maximal Metroids.
I mean, I guess like sort of the thing I noticed when I was playing around with you know, circuits of this like, you know, K4, K33 Metroid is that like basically every circuit you can sort of, you know, on up to like, you know, 11 vertices, or until I sort of ran out of patience and computational power, like you can tell that something is a circuit by finding either an almost K33 or an almost K4, which is, you know, a K33 without an edge or a K4 without an edge. So in other words, like there's always an edge you can add such that you can see like, oh, this is explainable in terms of like smaller circuits. And so what if you just add an edge, like just, you know, without being too strategic about it, like, or maybe there's always an edge you can add such that maybe here's the thing. Maybe you can always add an edge to your circuit such that the resulting graph is you know, too connected or connected in the Metroid sense. Then this gives you an ear decomposition, and you know that new edge is going to have to, you know, play some like pivotal role in it, right? And then this sort of like, you know, this gives you kind of like an induction step, right, where you can. And these are all.
Is this kind of what they do in the closure operator definition of the maximal Metroid, though? Because you sort of you're throwing in implied edges, aren't you?
Yeah.
The same way they do.
Yeah. I mean, it's that same. Yeah, it's a similar idea.
I mean, also one comment is that I strongly suspect. I know you're not talking about the rigidity Metroid. You're talking about this matrix completion one.
Yeah.
But so example, if you talk about the three-dimensional rigidity Metroid, then if you're very small, everything is just gluing K5s together and it's double banana kind of things.
Yeah.
But I think that's very much a very small graph property, and that if you're big enough, it won't be true that you just have K33 minus an edge and K4 minus an edge as explaining everything. There'll be much more subtle reasons higher up, I guess.
Yeah, I guess K55, right? That you can't explain.
Yeah. Well, that's a rigid circuit, but yes, things like that.
But yeah, okay, so if you stick an edge into K55, yeah, is what you get two connected?
Yeah, because it's got a spanning circuit. So you take K55 as the first one, and then any circuit containing the last edge as the next one.
Right. Okay.
I have to add up the numbers, but K45 plus an edge maybe is a circuit as well. I'm not sure.
Okay. All right. Okay. So the ear decomposition you get is not interesting because K55 is just going to be one of the circuits.
Yeah.
Okay. But I mean, maybe this can be sort of like a distinction between like possible complexities of these kinds of matroids, right? Like, yeah, like in the 2D rigidity matroid, everything is explainable in terms of K4, I guess. Or is that true? That seems true.
What I'm not quite sure what explainable in terms of K4 means, but probably if you phrase it the question rightly, yes.
Like you can always. No, you don't always have an almost K4, but you can always like. Every circuit consists of like you can take two smaller circuits overlapped in a certain way and then remove a single edge. Is that true?
I think that was a result of Ileana's from the workshop a couple of weeks ago.
Oh no, but those are okay. Or no, but she had the issue where those weren't always circuits, right?
In general, that move doesn't preserve circuits; it just preserves dependent. But she had some way around that I haven't found the paper yet to read.